Good afternoon. My name is Felicia Chow with the Office of Communications, and welcome to NASA headquarters. NASA has selected science instruments for the EUROPA mission as part of our commitment to explore the solar system and beyond, to understand the workings of the universe, and search for life among the stars. We will have brief presentations from our panelists. Then we will take questions from the audience, the phone lines, and social media. To ask a question using social media, please use the hashtag AskNASA. Today's participants are Kurt Niebuhr, EUROPA Program Scientist; Jim Green, Director of the Planetary Science Division. And to officially start us off, here is John Grunsfeld, Associate Administrator for the Science Mission Directorate. John?
Thank you very much, Felicia. We're on our way to EUROPA. Our mission is to innovate, explore, discover, and inspire. We're trying to answer the big questions. Where did we come from? Where are we going? And are we alone? These we translate into science questions. Ever since the 11 flybys by the Galileo mission more than a decade ago, we've been intrigued by this amazing moon of Jupiter. It's about the same size as our own moon, and scientists have scrutinized these images to incredible detail and determined that EUROPA harbors a deep, salty ocean below a thick mantle of ice. The images show a cracked, even tortured surface. I've just lost my notes. I get them back. One of the amazing features of EUROPA is that we see very few craters, indicating it's a very young surface. Something is causing it to be turned over. The age is perhaps only about 50 million years. Tidal forces from Jupiter must be causing some dynamics that result in the surface being in contact with that undersea ocean. Recently, observations from the Hubble Space Telescope, you knew I had to get Hubble in there somehow, detect what may be plumes of water shooting out from under the surface of EUROPA. This may be part of the mechanism that helps resurface EUROPA. EUROPA is just one of many icy moons in our solar system that are likely sites of subsurface oceans. For EUROPA, that ocean may have been in existence for billions of years since the creation of the solar system. In that ocean, of course, is water, salty water, organics, and likely sources of heat, such as undersea vents that we see here on Earth. All of those components are the kind of contributors that we believe are necessary ingredients for life to emerge. The instruments we're announcing today are the result of investments we've made over the last few years in technology to help interrogate the icy bodies in our solar system. The complement of instruments we've selected are compelling and will result in a mission that is every bit as impressive, in my opinion, as the Cassini mission to Saturn or the previous Galileo mission to Jupiter and its moons. The mission design is still being studied, but we wanted to get a head start on the instruments, as they're often the long poles in the development of something as complex as a mission to EUROPA. Jim Green will cover the science in some detail, and Kurt will go over the instruments we've selected. I'm incredibly excited about this big step forward in our quest to learn more about our solar system and the search for life beyond Earth. With some editorial license, let me quote John F. Kennedy from 1961 on the exploration of space. "This is the new ocean, and I believe the United States must sail on it and be in a position second to none. EUROPA, here we come." Jim?
Thank you very much, John. Yeah, EUROPA is just such a fabulous moon of Jupiter. In fact, much of what John described can be seen in our very first graphic of this beautiful moon. So as you can see, very few craters. It's has these brown areas, or what we call brown gunk, for the lack of really knowledge of what they are. And in addition to that, the brown also illustrates the cracks in the moon, where we believe the subsurface ocean must be communicating with the surface. This is indeed a fabulous body. As John mentioned, we've been studying it for a number of years, with only a few passes by the Galileo spacecraft, which was orbiting Jupiter in the 90s. And so ever since then, we've been intrigued by this body. Now, Europa was first discovered by Galileo in 1610. He never had the eyes that we currently have in looking and seeing this moon from the Galileo spacecraft named after him. Now, we are in the pursuit of trying to understand how thick that ice shell is. We know that there's an undercrust significant in terms of having more than twice the ocean. And in fact, that ocean might be significant in terms of having more than twice the water that we have on this planet. And after 5 billion years, with conditions like that, indeed, it could be a very habitable place if life indeed started on that body many billions of years ago. So what's underneath that ice crust? Well, we can only imagine, but we have, I think, some really good ideas and plenty of evidence to indicate that what I'm going to tell you about next is true. If I can have my second graphic. In this particular graphic, what we see is the moon Io and Europa in the background. We believe something like the surface of Io must be at the bottom of the ocean in Europa. So this is really exciting. Io is suffering the same tidal forces Europa is, although several orders of magnitude more extensive because it's so close to the planet Jupiter. Now, these hydrothermal vents really must represent the volcanoes that we see on Io, if indeed Europa has an ocean that is straddling the entire body. The hydrothermal vents that you see in these insets down at the bottom of the image are really our own from our Earth. And we know that they're full of life. They bring up nutrients, and those nutrients circulate through the ocean. So how do we know there are hydrothermal vents there? In my next graphic, we believe there's some really good indications of that. So at the very bottom of this graphic, we see what a hydrothermal vent might look like these volcanic eruptions that we have on Io must be at the bottom of the ocean. This is causing the water to be heated, massive circulation going on, and in fact that heat must actually go all the way up to the crust itself. Now, we don't really know how thick the crust is. We believe it's on the order of sometimes 10 kilometers. But in actuality, it may be only a few kilometers in spots. And in fact, we believe the cracks may open and close based on tidal forces, forcing water back out onto the surface. So as we see here in this particular graphic, that heat is transferred to the top of the ice shell. The ocean may be as deep as 100 kilometers. So if I have the next graphic, please. Here we see the very top of the surface, the ice crust, and what we see in the center is what we call a chaos region. We believe there's good indication that right below this chaos region is some of these hydrothermal vents. It's very consistent with our model of the ocean being heated from below and breaking up the ice, and in the cold environment that the surface of Europa has experienced, then ices over and produces these chaos patterns. We also see the discoloration of these particular areas, indicating that there may be organics or nutrients that is sulfur certainly that is filling these regions, and the discoloration is showing us. Now, on the lower panel on the right side is another process we also believe is going on. This is called subduction. This is where at a particular crack there may be one plate that's moving under another plate, also producing heat and possibly being able to produce plumes. Now, as you see in the upper right corner, as John mentioned, this is indeed taken from Hubble data. We've got indication that there are plumes at Europa, and Hubble has been observing Europa now for a significant period of time in search of what are the reasons that these plumes are occurring. So this is indeed a tremendously exciting opportunity, a time for us. And what I'd like to do now is switch to a little movie. As John mentioned, we've started the process of announcing our instruments for a multiple flyby mission of Europa. This particular movie, once we get her started, shows our concept of our spacecraft flying by Europa. It's actually orbiting Jupiter. We find that multiple flybys can allow us to get a complete picture of Europa after many flybys. Also, the opportunity of flying through one of the plumes. So the instruments that we're going to talk about today indeed set the stage for what Europa looks like in great detail on its surface. It tells us about how thick the ice is. It tells us perhaps how the under ice crust ocean is communicating with the surface through these plumes, and allows us to make these kind of detailed measurements over a long period of time. And so to understand what we've selected and to talk about each of the instruments, let me turn it over to Kurt Niebuhr. Kurt?
Thanks, Jim. We received 33 proposals from people interested in building instruments for this mission, and today we're announcing the selection of 9 of those to fly on the spacecraft that we eventually send to Europa. All of these instruments are designed to increase our rather limited knowledge of Europa, and they're doing that by helping us probe the big question, which is Europa habitable? That's a very difficult question to answer, and these instruments all pursue a different aspect of that big question. So if I could have the first slide, please. The first 2 instruments that we'll be talking about today are a magnetometer and a series of 3 Faraday cups. These are rather small and straightforward instruments that provide a very powerful and useful data set. What they allow us to do by measuring the magnetic field and the plasma environment of Europa in exquisite detail means that we can essentially take an MRI of the interior structure of Europa without actually accessing it. What they can do, if you look at the part in the lower right, that very complex diagram, what that indicates is that if we're very clever and when and where we take those measurements, what we can actually do as we fly by Europa is figure out how deep that global ocean is and how salty it is. And we can do all of that without actually cracking open the crust and dipping our instruments into the ocean, just as a doctor can see what's going on inside your body by using an MRI. Next slide, please. The next instrument I want to talk about is a special camera we call an infrared spectrometer. But this camera doesn't take pictures of the surface. Instead, it acquires something we call spectra, which are those squiggly lines you see on the right-hand side in the logo. Spectra are very beautiful things because they're not random squiggly lines. They're actually unique fingerprints that can tell us what materials are on the surface of Europa. So if we know that a certain material, say table salt, has a squiggly line of a certain shape, a fingerprint of a certain shape, and then this instrument shows us that fingerprint on Europa, what we then know is that table salt exists on Europa. And by cataloging the entire surface, we can get a near global map of the stuff that populates Europa's surface. We can know what it is made out of, and we can do that for almost the entire surface. Now, the reason that's important is because of that brownish gunk that Jim mentioned. And that is our state-of-the-art term for it, brown gunk, because we don't know what it is. We have a lot of educated guesses, but they're just that. They're guesses. We need actual data to be able to nail this material down. And this material is important because, as you see in the middle picture there, that brownish gunk is associated with the absolute newest, youngest areas on Europa's surface. These are areas where we think that water is erupting onto the surface just like lava erupts onto the surface of Earth. And this brownish gunk is what is being carried in that water. So if we can determine what that brown gunk is, we can then understand what is in the water, what's in the oceans of Europa. And that is an incredibly important question to answer if we're trying to figure out if this place is habitable. Next slide, please. So the next instrument is a camera, and it's actually a set of 2 cameras. There is a wide-angle camera that provides large images of relatively low resolution of the surface, and those images are in color. And then there's a narrow angle camera that provides very high resolution images. This is really a critical instrument for this mission, because the best pictures we have of Europa are from Galileo, the mission that John mentioned. And Galileo was a truly phenomenal mission, and is the mission that revealed to us that there's a global ocean on Europa. But we often overlook the simple fact that Galileo only flew by Europa about 11 times. It did not get a lot of pictures of Europa. When you sum all those pictures up, we've only seen about 10% of the surface of Europa at a resolution of 200 meters or better. That means that there is a lot of terrain that we don't really have good pictures of. But we have spent the past 15 years poring over those small number of pictures over and over again for two reasons. First of all, because they're the only pictures we have. And second of all, because they're such fascinating pictures. And you see examples of some of those on this slide. In the center, you see a picture of an area that looks like a cracked up jigsaw puzzle. We see regions on Europa where there are huge blocks, tens of kilometers across, that look like icebergs that have been melted out and have rotated and shifted. And you can actually look at this picture and you can reassemble that jigsaw puzzle and put those pieces back together. But something caused them to shift. We also see in the lower left-hand corner icebergs that are kilometers high with sheer vertical cliffs. And then in the upper right corner, you see these odd ridges that are ubiquitous on Europa. They are everywhere. And they look remarkably similar to the mid-ocean spreading ridges we see on Earth, where these are ridges that are pulling apart from one another, as in this case, water could be erupting from below and pushing the crust apart. These are the things we've seen just by looking at 10% of the surface of Europa. The instrument we selected today will cover almost 90% of the surface at 50-meter resolution. And if we've seen such amazing things on only 10% of the surface, it's hard to even imagine the amazing things we'll see when we look at the rest of Europa at even better resolution. Next slide, please. As John mentioned, we think Europa has a very young surface because there aren't a lot of craters on the surface. And if it's young, that means it must be very active. Something is causing that surface to renew itself. The next two instruments help us investigate that activity. Something is causing the surface of Europa to turn over, to generate new surface. What the ice-penetrating radar on the left here does is allow us to see underneath the surface of Europa. We can actually probe it in 3 dimensions. It allows us to see the structure and the layers of the ice underneath, see how those layers have shifted and bent and twisted. And what that means is we can see how they're oriented and get a better idea of how they have changed through time. This radar is also very good at detecting subsurface water. Recently, we have strong evidence that there are lakes underneath the ice crust on Europa, just as we have found over the past decade or so in Antarctica on Earth. And we think these lakes are incredibly common on Europa. This radar will be able to identify those lakes, tell us where they are, how big they are, how much water they contain. And this is important because these lakes are likely very close to the surface, which makes them easier to study. The other instrument you see on this slide is what we call the thermal imager. This is our heat detector. This is important because if there's activity going on the surface of Europa, that activity is associated with heat. That's what's powering the engine that's operating here. So finding the relatively hot spots can help us understand where and how Europa's surface is active. Hot spots being a fairly relative term. Europa's surface is about minus 160 degrees Celsius. We're looking for areas that are just a couple of degrees warmer than that. So we're still talking very frigid temperatures. So this is an incredibly sensitive instrument. But conversely, there might be areas on Europa, such as where plumes are erupting or where there's active eruptions of water, that might be 100 or even 150 degrees warmer than that. And this instrument will do a very good job of pinpointing those regions, some of which could be very small. And that's what you see in that simulated image on the lower right-hand corner. That's an image of one of those spreading ridges that we see on Europa. along with what we think could be the heat signature, the thermal signature, as it erupts new material onto the surface. And this thermal imager will be able to spot that activity very precisely. Next slide, please. Next, we come to our next two instruments that are composition instruments. These provide very detailed information on the composition of Europa using a different technique than the infrared spectrometer I already mentioned. The infrared spectrometer is looking at the entire surface of Europa, but what these instruments do is they actually ingest samples of Europa that have been blasted into space and directly measure them. The first one in the top left-hand corner is called mass specs. And what this does is essentially sample the atmosphere of Europa. But the atmosphere of Europa is really a misnomer. Europa doesn't have an atmosphere, it's a vacuum. So the materials we see around Europa are actually materials from the surface that have been lofted into space. And what this instrument does is analyze the composition of those surface samples, those gases, to an incredibly precise degree, better than we ever have with any other mission. Similarly, the second instrument called SUDA does about the same thing, but instead of working with gases, it's working with dust. It is working with very small particulates of rock and ice that have been blasted off the surface of Europa and lofted up to where the spacecraft is at. And working together, what these two instruments can do is measure the surface composition of Europa without actually having to land on Europa, which is a very powerful technique for us. But the real power of these two instruments is shown in the center picture here, which is a diagram denoting some of the chemistry that occurs on the hydrothermal vents on Earth's ocean floor. With these two instruments, what we can do is when samples from down there are lofted to the surface and brought to the spacecraft, these instruments are powerful enough and precise enough that they can actually, from orbit, teach us about the chemistry happening at the bottom of Europa's ocean without actually having to dive into that ocean. These are techniques that we've used very successfully on the Cassini mission to understand Enceladus and its ocean and its plumes. The instruments that we'll be taking onto Europa are several generations more advanced than what we have an idea of how they have changed through time. Have on the Cassini mission. Next slide, please. And finally, we have our Plume Hunter, an ultraviolet spectrograph. This is an instrument that is specifically designed to find the plumes that we recently discovered and that we're so interested in. Every one of the instruments we're flying does plume science. It tells us about the plumes. But this is the instrument that's specifically designed to hunt them down and tell us where they're at. This instrument uses the same technique that the Hubble Space Telescope used to first find evidence of these plumes. And as we are flying both near and far from Europa, it will identify where those plumes are, how active they are, what kind of materials they are spewing into space, and how they vary with time. Because as John mentioned, we're already seeing evidence that these plumes change with time. They start, they stop, they move, they start up again. The dynamics of these plumes are very complicated, and we don't understand them yet. So bringing along an instrument that can observe those plumes and give us an understanding as to where and why they pop up is incredibly valuable. Next slide, please. So this is a very wonderful set of instruments. But recall that the big question that this mission needs to answer is Europa habitable? Posing big questions like that is very easy, but answering them is much more difficult. So what we need to do to answer that big question, is Europa habitable, is break it apart into more manageable chunks and to smaller questions that we can answer definitively. And finally, definitively. And those are the questions listed here. These are the questions that the next mission to Europa must answer. Because once we have definitive answers to these questions, we can then attack the bigger question of, is Europa habitable? So once we know how deep and salty that ocean is, we can get a better understanding about habitability. Once we know how thick the ice shell is, and to what extent it communicates with that ocean and brings material up to the surface and material back down into the water, we can have a better understanding of whether or not Europa is habitable. Once we understand how active the ice shell is and how it is behaving with time, we can better understand habitability. And once we understand what that ubiquitous brown gunk is, we can understand what one of the direct components of that ocean is. All of these things feed into that habitability question. And finally, one of the most recent questions that we've begun struggling to answer is, where are those plumes? What's in them? Are they really delivering samples of the ocean to us in space that we can easily access? And if that's the case, how can we get at them, and what kind of measurements can we take on them? This payload will answer all of these questions and help us take great strides forward in understanding the habitability of Europa.
Thank you, Kurt. Now let's go into the Q&A session. If you'd like to ask a question using social media, please use the hashtag AskNASA. So before we take questions from social media, let's see if there are any questions from the audience. Okay, please wait for the mic and say your name.
My name's Katie. Hi. So, if you were able to detect any form of life, what would be the next steps that you would take in observing Europa?
Okay, I would immediately retire. That's I've been telling everyone that answering that big question is there life in the universe really starts from understanding if there's life in the solar system. Europa is one of those critical areas where we believe the environment is just perfect for potential development of life. And so this mission
Here, these are the questions that the next mission to Europa
helps us understand the environment and hopefully give us an indication how habitable the environment could be. If we do find life or indications of life, that will be an enormous step forward in our understanding of our place in the universe. If there's life in the solar system, and in Europa in particular, it must be everywhere in our galaxy, and perhaps even in the universe. So understanding these questions are important because they have really a major implication to our understanding of our place in the solar system and in the universe.
Hello, Nathan Ross, and you mentioned chaos regions, and could you go into a little more detail on those, like what those are?
So in the one graphic where we saw a place on the surface of Europa as a chaos region, it's my third graphic, third graphic there. What we're seeing, we believe, what's underneath that chaos region, perhaps a melted lake region, and below that it's being heated by perhaps a hydrothermal vent at a depth that we don't really know. Depends on how hot the thermal vent is and how close it is to the ice crust. And so, as Kurt mentioned, one of the instruments, which is an ice-penetrating radar, we want to target these regions. We want to fly over. We want to see these broken up ice sheets, if you will, creating these chaos regions, and see indeed if there's they're very thin, perhaps there's a lake underneath it, perhaps either they're completely open to the ocean below, or maybe there's a bottom to them. So in this graphic, it proposes an under ice thin crust of melted water.
Thanks, Jim. Let's go to the phone lines and then social media. First on the line, we have Irene Klotz from Reuters. Irene?
Hi, thanks very much. I have several questions. The first is, Jim, if you can maybe just give us an overview of the funding for the Europa mission, both NASA's request and the very much more money that Congress seems to be interested in putting toward.
And hopefully give us an indication how habitable.
And the status of the proposal to put a lander on it. And also, if you could give us a little rundown of how much the 9 instruments plus the technology demonstration, the 10th one that right now isn't slated for the orbiter or the Clipper, how much NASA is going to be spending on all those. Thanks.
Okay, so let me see if I can go through all of those and pass off a few to my colleagues here. One of your first questions, indeed, was what about the mission itself? As we announced in February when the President delivered his budget to Congress, we have indeed a projected budget for the Europa mission out over the 5-year projected budget that the President provides. This is a tremendous opportunity for us to really get serious, complete our initial studies, and move the mission into what we call formulation. So it's not only important to know that we're moving towards that, the instrument selection is the start of that process, but our plans are to have this key decision point of starting the formulation before the end of this fiscal year. Now, how much is the total mission cost? That I think was your next question. We have some mission concepts, some basic mission concepts that we are exploring in great detail that mean that the mission perhaps is on the order of $2 billion without the launch vehicle, in that neighborhood. But what's important to understand is now that we've made the selection of the instruments, we're going to begin the accommodations on our mission concept. We're going to move the whole activity into formulation and get really serious about all aspects of the mission. We won't really have a detailed understanding of what that cost profile is until we are further along in the process. And so to another one of your questions is how much is the instruments and what have we selected costing? And for that, let me turn it over to Kurt Niebuhr to give you an idea of the costing. And for that, let me turn it over to Kurt Niebuhr to give you an idea of the cost on the instruments.
So over the next year or so, we'll be spending about $10 million total on the instruments. And over the next 3 years, it comes to about $110 million total on the instruments. That'll get us to the point where we reach a key decision point where we decide if we're going to continue on with the instruments, if some of them are no longer ready and we need to revisit them. But in about 3 years, we'll be ready to commit to the full cost estimate for those instruments.
Okay, we'll take one more question from the phone lines before going to social media. Next, we have Jeff Faust from Space News. Jeff?
Hi, sort of a related question to Irene. This one sort of on the schedule. The House is pushing a fairly aggressive schedule in its appropriations bill seeking to launch a Europa mission by 2022. Is it reasonable that these instruments selected today would be ready for flight by 2022? Thanks.
Given the schedules that the instruments provided us and the time they need, they could be ready in the early 2020s, but that's also dependent upon how much money is in the budget for us to give them for that work.
Okay, we'll take one more question from the phone lines. This is from Mike Wall of Space.com. Mike?
Yeah, hi guys. Thanks for actually doing this. So there are no explicit life detection instruments on this mission, right? Could any of these instruments theoretically find some signs of like dim alien life, if any does exist on Europa? And if that's the case, what sorts of things could it be capable of actually picking up?
Well, actually, that's a great question, and the short answer is they could find indications of life, but as you said, they're not life detectors. And in discussing this question over the past several months, what became clear is we don't have a life detector. We currently don't even have consensus among the scientific community as to what we would measure that would tell everybody with confidence this thing you're looking at is alive. So building a life detector is incredibly difficult. We're not really sure how to go about building it yet, but it's something that has received renewed interest and vigor lately because of the Europa mission. So that's something that we're going to be poking into a lot more aggressively in the near future.
Thanks, Kurt. Next question we have is from Ken Kramer of Universe Today.
Hi, thank you for taking my question and doing this briefing. I have a few questions about the science instruments. One, I wonder, depending on the budget, could you add more? I'm also wondering on the mass spec, can you talk a little bit about what's the mass range that it can detect? Is there a chiral analyzer that might be aboard? And about the flybys, how many do you expect to accomplish, and how long would they be? Thank you.
The issue with the number of instruments isn't so much money, it's real estate available on the spacecraft. You've got to have room to bolt them onto the spacecraft. You have to have the mass available to fit them onto the launch vehicle, and you've got to have the power available to turn them on. So those are the primary considerations that drive the size of the payload as opposed to the cost. You asked about the mass spectrometer. This mass spectrometer, the mass range is from 1 to 1,000 Daltons. To give you an idea, the Cassini mass spectrometer is between 50 and 100 Daltons, depending on what mode you have it operating in. And the mass resolution of this mass spectrometer is also phenomenal. So it's an incredibly capable mass spectrometer. And then your last question, I'm sorry, what was your last question?
Chiral analyzer and also about the flybys, how many you'd be doing.
We don't have the ability to detect chirality with the payload we selected. And right now, the baseline mission, we're looking at about 45 flybys of Europa.
Great, thanks, Kurt. Now let's go take some questions from social media. Here is Jason Townsend from our social media team. So what kind of questions are we getting on social media today, Jason?
We're getting a wide variety here. Following up on the last question here, Casey Dreyer asks, how does the resolution of the mass spec instrument actually compare to the mass spec on Cassini, and what could you detect that Cassini can't?
I won't bore you with the numbers. The comparison to the resolution of the mass spec for Cassini is that there's really not much of a comparison. The mass spectrometer on Cassini was excellent for when it was built, which was the early 1990s. The mass spectrometer that we selected today is very advanced, and it has benefited from a significant investment from NASA over the past 4 years as well. So the mass spectrometer mass resolution for what we selected blows everything else out of the water, and that's why we selected it.
Wonderful. Next question comes from Jason Major, who asks, what is the anticipated launch date for a Europa mission? How long would the trip take, and how long could the mission run?
So right now, once we move it into formulation, we expect it to be launched in the 2020s, whether it's mid or a little early or a little later. Needs to be worked out based on a much firmer cost estimate and a profile that would support it. That's what formulation is all about, is putting all those resources together and
all right, this next question,
getting serious about a major design as we move forward.
All right, this next question comes from Twitter user Bradley, who asks, what drove the decision to go straight to a 9-instrument mission complement and skip a Phase A down select?
Originally, we had considered doing what we call a two-step process, which means that if you're going to fly one camera, you select 2 or 3 or 4 of them. And you give them some money and some time to do some work to reduce their risk, address their technical challenges. What we found when we reviewed these proposals, though, is that in every category of instrument we wanted to fly, there was one that was ready to go now. And in fact, in most cases, there were more than one that were ready to go now. So we didn't have any instruments that needed additional work. We had instruments that were ready to move into formulation right now with a high degree of confidence that they would be ready for flight in the 2020s.
I think part of that is because we did invest over the past few years in a technology program for icy worlds to be ready for this next step. And we found that, in fact, that has been highly valuable and has allowed us to go to a one-step process.
Wonderful. Next question comes from the Ustream user, Sergio, who asks, is laser communications going to be used in this mission?
Currently, the baseline mission doesn't utilize laser communication. That would be deep space optical comm, really deep. We've tested it from here to the moon. We haven't even tested deep space optical comm from here to Mars. And of course, Jupiter is, at 5 astronomical units away, where the Earth is 1 astronomical unit away. And so we have a lot of work to do to be able to utilize optical communication for these outer planet missions. But that is a wonderful set of technologies we would love to have in our hands today. And Space Technology is indeed, Mission Directorate is indeed working with us to invest in this particular area. But the next stop will probably be Mars instead of Europa for deep space optical comm.
One of the challenges to keep in mind when we go to Europa is that Jupiter's magnetic field is an accelerator of charged particles. It's kind of like the sun itself. There's a Jupiter wind. And so the radiation environment at Jupiter is fierce. And so as we look at the technologies to support the mission, we want to take low risk on the spacecraft so that we can put most of our effort into the instruments, which also have to survive in that high radiation environment. So laser comm is probably a little bit early for Europa.
Mm-hmm.
Thanks. Let's take 2 questions from the phone lines before going back to social media. The first question we have is from Mike Delfiore from Popular Mechanics. Mike?
Hi, thanks for taking my question. I just wanted to follow up on the mission duration, the length, that you mentioned 45 flybys. And someone else had asked the question how long it might take, so I was interested in that. I'm also interested in where the instruments are being built and when they will start being built.
Well, mission duration, once we get to Jupiter, we'll spend about 2.5 years doing those 45 flybys. So at the fastest pace, we have a flyby about every 2 to 3 weeks. In terms of where the instruments are being built, it runs the gamut. It spans the country. We have instruments being built on the West Coast at NASA centers. We have instruments being built in university labs. We have instruments being built in federal research labs as well. So it really spans the country. When will they be built? As far as I'm concerned, they start tomorrow. And they're going to be working very hard every single day until we get this mission to the launch pad. And then they will actually start working harder, because then we need to start flying these instruments and operating them.
One of the things to understand about the mission architecture is the multiple flyby concept. This particular mission that we're moving towards, to stay out of the radiation belt and only be in it as we need to in taking extensive data about Europa, actually orbits Jupiter itself. And so as it flies by, it takes a massive amount of data, and then as it moves out of the radiation belt and is clear, it then begins to send that data back in full resolution. Now, this is really a spectacular way of managing the data. It allows the scientists to get all the details to really tease out everything that we want to. It also allows our plume chasers, so to speak, to really continue to look at Europa and find potential plumes that on the next pass we could potentially fly through. So the architecture is set such that we maximize that time when we're away from Europa by getting set up and aligning ourselves again for the next flyby to maximize the science that we want to do.
Thanks, Jim. We'll take one more question from the phone lines before going to social media. This is Irene Klotz from Reuters.
Thanks. Kurt, could you maybe elaborate a little bit on what you would consider indications of life with the suite of instruments that were selected? What sorts of things might be indicative of life? And also, is there room aboard the spacecraft for all 9 of these instruments to fly, or would some need to be eliminated for mass purposes?
I'll take your easier question first. Yes, there's room on the spacecraft for all 9 instruments that we've selected. That was one of the criteria that we looked at when we made the selections. Your first question about what are some of the possible signs of life we might be able to detect is a very difficult question because we're not sure what those signs would be. I mean, it would be wonderful if we would see chlorophyll like you see in earth plants, but we're not going to see chlorophyll. Mother Nature is not going to be that kind to us. It would be great if we would see fossilized bones sticking up out of the surface. That's not going to happen. Mother Nature is not going to be that kind to us. Finding evidence of life is very nuanced. It's very delicate. It's very difficult to do. Even if you go out to a lake or Earth's ocean and grab up a scoop of water, signs of life don't immediately jump out at you. So it's going to take some very smart people sitting around working together over the next few years to build upon the work that has already been done to help educate us in this area.
Thank you. Now let's take a few questions from social media. Jason?
Sure. Twitter user Dave asks, are there any instruments from this payload that could work with instruments from ESA's JUICE mission?
Yes, there are. In fact, the ultraviolet instrument that we selected is a contribution that NASA is also making to the JUICE payload. They're very similar instruments. So there is overlap among both of the payloads, so they complement one another strongly. But I think it's important to keep in mind that the JUICE mission that ESA is putting together, its focus really is on Ganymede and to a lesser extent Callisto. They're only flying by Europa twice because of the nature of their mission design. We'll be flying by Europa 45 times or more.
Wonderful. This next question comes from Dr. Leo here, who asks, what kind of propulsion and craft will take the instruments mentioned to Europa? And additionally, Twitter user Crow asks, what will be the power source for the spacecraft?
The spacecraft will be solar powered, so we're going to have solar panels on this mission, just like we do for the Juno mission, which will reach Jupiter in about a year. In terms of the type of spacecraft, it will be chemical propulsion, so pretty standard propulsion systems that NASA uses for the majority of its science missions. We will burn the engine hard, we'll burn it hot, and we'll get there as fast as we can.
Wonderful. This next question comes from Twitter user Ryan, who asks, is anything actually landing? And if so, will it be able to send a probe into the ocean?
So at this stage, we are doing some studies, and very elementary studies, about landed missions. You know, in planetary science, we make a very important progression of flyby, orbit, land, rove, and then return samples. And we do that in a very deliberate way. And although Galileo gave us the tantalizing glimpses of what Europa is like, the multiple flybys of Europa will give us the orbital view, will give us a global understanding. To be able to get down to the surface is a huge step after that. We don't really know in any detail about how hard it is to land on a very corrugated surface or where we would need to go. We have an extensive amount of research to be able to do in that particular area. And although we're studying that at the moment, the results of those studies won't really be known to us until later on this year.
And I think it's important to keep in mind, I mentioned that Galileo gave us a limited amount of pictures of the surface of Europa. We actually don't know what the surface of Europa looks like at the scale of this table, at the scale of a lander. If it's smooth, if it's incredibly rough, if it's full of spikes. Without knowing what the surface even looks like, it's difficult to design a lander that could survive. So that's something that we have to take into account as well.
Well, following up on that, Twitter user Hamang asks here, will there be any robotic mission to Europa in the future to explore life, if any, or any of the liquid ocean beneath the solid icy surface?
Yeah, it would be great to think that the results from this particular mission would lead in the next decade to some new and exciting concepts about potentially getting underneath the ice shell. Once again, we need to really make those steps, methodical steps and scientific understanding to determine indeed if this body can be penetrated in a way to be able to get under the ice shell. But that's indeed in the distant future.
Wonderful. Last question here comes from Jason Major, who asks, would this Europa mission be able to acquire data on other moons and Jupiter as well?
It can. These instruments are fairly versatile. They're very much designed to operate on that flyby mode that Jim mentioned, because this is the multiple flyby mission, the MF mission. But if we choose to point these spacecraft at other targets like Ganymede or Callisto, these instruments would work there as well.
Okay, and that's all the time we have left for today. Keep those questions coming with the hashtag AskNASA. All the information you've heard today and more is available at go.nasa.gov/Europa News. Thank you all and all the panelists for joining us, and have a wonderful day.